Hello everyone, my name is Roman and I'm software engineer in Tinkoff, and today I appreciate the ability to be here, and let me introduce Adam Furmanek. He is an expert in many areas such as backend, frontend, ML and databases. Hi Adam, how is it going?
Hello. Good. How are you?
Oh, I'm fine too. Today is a great day to know something new about login and house, I think.
It is, yes, exactly right time to discuss those things. And the right time is actually a very good phrase for today's talk.
Okay. I want to remind our attendees it would be great to send feedback, vote for the talk, and of course, use chat for questions to Adam. I know that you have prepared an interesting talk, and so I suggest save time and get started. What do you think?
Okay, up to you. We can go ahead. Cool. So, hello everyone. My name is Adam Furmanek, and today we'll be talking a little bit about time, as it was already mentioned. So, in this next 60 minutes, we'll try to see how to order the chaos a bit, how to use time in computer systems, how to use wall clocks, or maybe what else should be used, should we use instead when we are talking about distributed systems, about clusters, about computing things across the world. So that's the plan for today. We want to see how to get some mess out of the picture and get some better logging. At least that's one of the use cases we'll focus on. Before moving on, a couple words about myself. I'm an engineer with over 10 years of professional experience now, also blogger and book writer. I wrote two books, one about .NET internals, feel free to take a look at it at Amazon, and the other one about applied maths, are actually the math domain, which is called integer linear programming. So feel free to take a look at those two. Drop me a line on email, Twitter, whatever works for you. If you had any questions after this talk, also visit my blog at blog.adamfurpanek.pl, where I cover things like from various areas of computer science, including .NET platform, but also other platforms or computer science in general, maths as well, and other stuff. Okay, so the agenda for today's talk is we are going to see what is time. So that's the beginning. We'll understand what the wall clock is, what the clock itself is, how we can use it in the computer science, how we can synchronize computers, how we can actually, what protocols we can use to share the time across all the nodes. Because our goal, our main idea for today's conversation is we are talking about a heavily distributed system. So we have nodes scattered around the world, once in some in the US, some in Europe, some in Australia, whatever you imagine. And all those nodes are actually processing something together, like one single workflow. And something may go wrong on the way, like that's the general idea that something breaks, or we just want to get some more insight of how things are working under the hood. And we would like to get some meaningful logs out of the process. We would like to get some messages which are actually structured in a way allowing us to understand what was the order or events, what happened like when we were processing things as we went through the code base. And this is where we begin. And we'll try to understand that just using wall clock to timestamp our events may not be a good idea, may not be enough when it comes to computer science. So later we'll see what we can use instead, what we should avoid, and what we can use in order to imitate or to emulate a logical wall clock in the computer system. Then we'll see some actual implementation showing you the code doing the job we'll be discussing today. And ultimately, at the very end, we'll have a couple of minutes of discussions what else we can do based on the basis we built today. The QR code you've seen on the first slide points to the slide deck. It will be at the very end as well. So feel free to download those slides and follow me or just watch them later as we go. So the section begins is what is time? Well, the thing we need to understand is there is no one global time. Whenever we as humans, when we speak about time, we are used to like the imprecision we have. It's okay if we just give time which is like a minute apart or 2 minutes apart. That's typically okay. So obviously there are scenarios where we need to be a little more precise, like when we are going on a train and we just want to be aligned with the schedule. But generally most of the times it's okay when we are not super precise and we can just pretend like there is one global time which we are using. However, when we are talking computer systems, when we start using the time in distributed systems, we can't pretend that it's okay anymore. We just can't do it because we need to understand that every machine in our cluster, and we are talking about like machines scattered around the world, as already mentioned, all of them observe different time. Well, first, all of them have their own physical clocks, and just the clock may work on like a different frequency, may have different precision, may be tuned or adjusted to some different value, which in turn gives different readings. Second, there is again a delay between like reading the clock or just calling the API asking for what's the time and getting the actual answer and then processing it later. So this delay introduces yet another thing here, that when we are talking about high precision, we just can't rely on physical clocks because they are not that precise. Technically, what we want to achieve is like precision in a matter of nanoseconds. This is something we cannot do. The best we can do is probably in terms of like milliseconds. In very rare cases, that could be microseconds. Again, there is yet another thing when it comes to time, which is like general theory of relativity, right? And special theory of relativity. When we are traveling with very like high speeds, then well, we perceive the time a little differently than people in like different places of the world or the cosmos or whatever. This is something we need to take into account when we are talking about like computers like GPS or positioning systems in general, when we need to synchronize the time, and all those cosmological phenomena can already be like observed and measured. Like when we are talking about like a space station running out there up in the air, it perceives time differently than what we have here on Earth, and we need to take that into account. We're talking about the wall clock. Again, another thing is that well, clocks do break over time. It's just obviously they do have some precision, and as we go the precision like deteriorates. Okay, so we call it a time or clock drift. So they have a drift, meaning that after some time they just go out of schedule, out of sync, and we cannot just rely on them anymore. When it comes to technical definition, what's the time? Well, the answer is like periods of transition of some cesium, which is so completely not interesting for us. However, what is important is that there is an official definition, and the atomic clocks which we use across the globe, they adhere to that definition. I mean, they just use the very specific definition and the very specific physical implementation to run those clocks, and this is something we may want to be aware of. However, for our talk today, it's completely unimportant how the clock is realized on like the physical level. What is important is only the clock reading. And there is one more thing which we typically connect with all the clocks, which is UTC, like coordinated universal time. This clock or this measurement is based on the atomic clock, and it's synchronized and broadcasted regularly, meaning that when we have machines around the globe, they need to be synchronized together so they pretend they have exactly the same reading. We'll see a little later how they can be synchronized and whether it's entirely possible. However, the idea is that all those atomic clocks, they show exactly the same time. And also, they broadcast this time to their neighbors, and we can get to about 1 microsecond of precision, something we can get with atomic clocks. However, something which is not physically or not effectively usable for us because of all the delay being introduced across multiple layers of like software and hardware. The best we can get is should be rather measured in milliseconds, not microseconds. But moving on, we have time, but there is yet another super important term, which is called a time zone. So what is a time zone? Well, it's not only a UTC offset, even though that's what we typically think about. A time zone, technically, is a region of the globe which observes the same standard time, meaning that it has exactly the same clock reading, but also it has exactly the same rules when it comes to how we change our clocks. This is when it comes to like daylight saving time, or this is when it comes to other transitions between like UTC offsets. They all need to be specified and they all need to be shared. So the region of the globe which observes the same time and the same rules is actually a time zone. UTC offset is not enough to specify a time zone. But when it comes to the UTC offsets, typically we think that they are like full hour from midnight, right? So we say that UTC offset is +2, +3, -7, depending on where you live. However, that's not only the case. There can be offsets which are like +5 hours and 30 minutes. That can also be other UTC offsets, even down to a millisecond. Also, they can change over time. So this may be also interesting that this is not something which is like constant across the globe or constant in given part of the world. This is something which changes as we just move on, and we'll get to that a little later. The most important stuff when we talk about time zone and how it can break our computers is the thing called daylight saving time, DST for short. So it's this time of the year, like it happens twice a year, when we typically move our clocks like 1 hour ahead or 1 hour behind, right? This is what we do, and this can happen at various times of day depending on where you live. It can be that, for instance, you move your clocks at 2 a.m. or maybe at midnight or maybe 5 minutes after midnight. It also depends on the where you live. It depends what time of year is when you move your clock. So for instance, Europe typically moves its clocks a little earlier than the US does, or the opposite if we are switching back to this to the winter time. So generally, all those things are important for us, because when we start talking about distributed systems and computers across the globe, we need to stop thinking that there is just one time zone, and it works exactly the same. No, we need to understand that not only there are multiple times around the world because each computer has its own, but also when it comes to the local time, it highly depends on the culture, on the region of the globe, and other stuff. And when can this bite us? Well, one of the things which is relatively straightforward is, imagine that you are trying to book a plane ticket 6 months from now. Okay, so it's June and you are trying to book a ticket for December. Now, in December, most countries will be in winter time, right? So we'll need to move our clocks like 1 hour, 1 hour behind. Now the question is, when we do open up a calendar on our mobile phone today, and the plane departs at 8 a.m., should we show it in the calendar, our calendar, as the event is at 8 a.m. or maybe 7 a.m. or maybe 9 a.m.? Because if we put it at 8 a.m., then 6 months from now it may move back 1 hour because of the summer to winter time transition. But if we show it like 9 a.m., because then it will be moved back 1 hour, then customers may come to us and say, hey, I booked a plane ticket for 8 a.m. and it's showing me 9 a.m. What's going on? And even though we may understand what's going on, customers may be surprised. So time is tricky. But it gets even trickier when we start discussing the details. So time zones do change in history. For instance, in Europe, Warsaw, where I come from, there were multiple different time zones across the years. So for instance, in 19th century, so when we had like 1800s until 1914, what we had at the time zone was, or the time offset was, UTC plus 1 hour and 24 minutes. Pretty weird, right? But then it changed a couple of times whether we did have daylight saving time or not. We did have it, then we didn't. We dropped it, then now we have it again. And now European Union is considering dropping it one more time. So it may be that those things will change. So when we are talking about things in the past, this is actually getting super tricky to calculate the local time. However, when it comes to things, how those time zones are spread across the world, it also gets interesting because depending on the country, no matter how big it is, there is like no single rule. It may be that your country runs on multiple time zones. It may be that it runs on just one of them. For instance, China, which is pretty big country, it has just one time zone. However, the United States, they use multiple of them. So this is depends on where you live, but not only where you live, but also who you are. For instance, when it comes to the daylight saving time, uh, in the United States, most of the states do observe it, meaning that they do move their clocks twice a year, unless you live in Arizona. If you do live in Arizona, then you do not observe a daylight saving time. You don't move your clocks unless you are a Navajo tribe. If you happen to live in a Navajo tribe, they do observe a daylight saving time. So it's not only where you live, but also who you are. And also, it gets interesting even more that there are multiple towns around the planet for which one end of the town is in different time zone than the other end of the town. It's even more interesting in Australia because in New South Wales there is an airport for which the runway, one end of the runway, is in different time zone than the other one. So when when your plane departs, like right after you touch, you leave the ground, you change the time zone because it's the other end of the runway. So those things can be super interesting and can be surprising, and it goes on and on. For instance, Amsterdam once like its time zone or UTC offset was 19 minutes 32 seconds and 13 milliseconds or 130 milliseconds. So it was generally simplified to 20 minutes because no one really cared. Offsets also goes from minus 12 to plus 14. If you ever thought that it goes from minus 12 to plus 12, which is like reasonable, then you may be surprised because Kiribati is like an island which is on the very far left of the map, so very far west. However, they wanted to observe like the New Year's as the first place around the planet, so they just moved to plus 14, which should be on the very far right. Okay. There are also, again, multiple different things depending on whether we are talking about like a civil time or maybe nautical time, or maybe we are talking about trains running on different time zones. It changes. It definitely changes. And like local time is definitely something we shouldn't be relying on that much. However, this gets even more interesting when we look at the definitions. UTC is like a time based on the atomic clock. So it's a time which is synchronized and distributed across the world. However, we typically think that UTC and GMT, they are the same, but they are not. GMT is a time zone based on rotation of the Earth, meaning that it can differ from the UTC by even almost 1 second. And that's why we introduce leap seconds to the UTC. We need to add leap seconds, or technically we can even remove leap seconds, but this never happened, but is allowed by the standard. And we remove those seconds or add them to keep UTC and GMT in sync. So they show more or less the same time, but they are not synchronized by definition. They can differ by definition. And leap second, well, it's added in various times of the year. It's obviously standardized and defined by some committee when it's added. However, once it's added, it can break your system. For instance, in 2012, when it was added, like the leap time was added, meaning that there was a minute which had not 60 seconds but 61. What happened is that Linux kernel couldn't handle it that well, and it caused a like CPU hog for an extensive time. So it just broke multiple computers around the planet. What we do instead since then is we do not add a leap second just as it is. Like we don't add a second so a minute has 61 seconds. What we do is we do a time smearing. So we just get this 1 second and smear it across multiple hours of the day. So we add millisecond here, a couple of more over there. So it doesn't like kill the CPU and it just increases the time like gradually. So this is what we do to avoid issues which we already observed and we've seen things break. Now, when it comes to distribution, how is time distributed? Well, obviously, there is some committee and there is an authority called Internet Assigned Numbers Authority, IANA for short, which publishes a database called Time Zone Database, or TZ, or Zone Info for short. It's updated multiple times a year and is obviously RFC'd, and most Linux distributions use TZ data package. So whenever you want to get new version of the TZ database, you just update your system packages and you are good. And this database includes everything about times and about time zones and about the regions and how it should be assigned. But obviously, it's computer science, so IT, we just can't go with one standard covering all of that. The other competing standard is called CLDR, Unicode Common Local Data Repository, which not only provides time zones, but also languages, locales, parsing formats, and other stuff. And CLDR, on the other hand, is used mostly by Microsoft, by Apple, by Google, and by other companies. And it's distributed again multiple times a year. But what is worse is it's not synchronized with TZ info, meaning that if you have like heterogeneous clusters or your applications, some of them run on Windows and some of them run on Linux, that you may, and you start querying the databases regarding the time zones, it may be that some hosts will already see some changes which were like politically standardized, and some others will not because one of the databases was not updated yet. What's worse, it's not easy to translate one CLDR into TZ info or the other way, TZ into CLDR, because there is no one-to-one mapping. Obviously, you can do some string typing or string mapping or string matching, whatever, but generally it's never guaranteed to work and it will probably break for like some time from now. So generally, this does not make things easier, and using this time is just, well, tricky. However, let's imagine that we do want to use the time, like local time, wall clock, the thing we see on our clock. Should we go with local time or UTC? Well, after hearing what I just told you, you may be thinking UTC is a silver bullet, and that's obviously what Stack Overflow is going to tell you. However, it's not. Imagine that we want to organize an event in like May in 2024, so let's say 2 years from now, and this event should start at 9 a.m. in the morning, okay? And the expected time zone of given place is UTC plus 2. However, let's say that at some point in the future, we don't know when, but let's say that the country decides to drop the DST, drop the summer time, and they do not use it anymore. So from now on, or from some time in the future, from a day in the future, they use UTC plus one at summer. So what happens if we store things as UTC? Then we'll get an issue, we'll get an error, because we get an event which is supposed to be scheduled for 9 a.m. in the morning, okay? So because it was UTC plus 2, we want to store it as UTC. So we subtract 2 hours, we get 7 a.m. and this is what we store in our database, okay? But then country decides to drop the DST time, 2 years passes, and what we have is we now get the day, we get the date, it's 7 a.m., we get the time zone, it should be UTC plus 1, or we get the UTC offset, it should be UTC plus 1. We add 1 hour to 7 a.m. and we end up with 8 a.m. So pros of this approach, well, it's super easy to implement, but the cons is it just doesn't work. If you store thing as a UTC and you do not update it anymore, then at some point in time, your dates may be just wrong. Now think for a second about all your computer systems you have implemented so far. In which of them have you considered things like this, and in which of them maybe need some adjustments to handle dates better? Okay, so maybe instead of storing UTC and never updating it, we can do something about this. And the idea is, well, we can update the date when we get a new TZ info or new CLDR version, okay? So again, we get 9 a.m., subtract 2 hours because this was UTC plus 2, we get 7 a.m. And then an update comes for TZ database. So we now recognize, okay, it was UTC plus 2. It was supposed to be a UTC plus 2, but now it's supposed to be UTC plus 1. We need to recalculate the time in the database and recalculate it from 7 a.m. to 8 a.m. So pros of this approach, well, it works. That's a good point. However, cons is, well, we need to think about recalculating all the dates. holding or storing a TZ info for which we store the date, right? Now we also have CLDR database. Maybe it's getting even harder when we are talking about things in different environments, okay? We need to remember when to update those dates, how to update those dates. So generally it's tricky, okay? But this algorithm will just give us a correct result, so this is good. But yet another approach we can take is we can just store the time as a local time. And I'm not talking here about like date time object or Gregorian calendar or whatever your language supports. All I'm talking about is something like conceptually stringy thing telling you that, hey, event is 9 a.m. because this is what customer gives us, right? Customer comes to us and says, I need this event to be at 9 a.m. And if we store it as like a business piece of information, then we can do whatever is needed. So this will work because we know the time and we can recalculate it on the fly whenever someone asks for it. However, consequences and like drawbacks are that we need to, when it comes hard when it comes to caching the result. And also we don't know what the data type to use for this. We don't want to store this in string, but what other data type is provided by the standard library? Who knows? Know that stuff. So generally getting trickier, but well, there is not a simple answer for this problem, and the problem is very real. There are also other problems with time. All those statements on this slide are purely incorrect. Like if you think minute has 60 seconds, that's not true. Year has 365 days, that's not correct either. So generally, all those things are like falsehoods we all believe, and I recommend you take a look at the link here about like programmers believe about time, and just understand that those things are not that straightforward as we used to think. Let's go through just a couple of examples. For instance, a month begins and ends in the same year. Not true. For instance, when the Gregorian calendar was introduced, then, well, obviously, the first day of the very new year was like sometime in the middle of the year. Effectively, this lead up to the situation that, well, the new year was not right at the beginning of the year. It was just in the middle of new year. Something like with Chinese calendar, right? They observe the new year a little later than we do, and this is a similar situation here. February has 28 days. We obviously know there is February 29th, like every 4 years or something. However, in Sweden in 1712, it had 30 days. Why? Because when all countries in Europe were introducing Gregorian calendars, they did it by skipping something like 11 days or so they had. However, Sweden decided, okay, we won't be doing that. We'll gradually catch up by skipping February 29th every fourth year, okay? But then the war started and they just did it like too many times, so then they had to roll back and they did it by introducing February 30th. So this is what happened. A minute lasts 60 seconds or something like that, unless you are running on KVM supervisor, which had a very interesting bug that when you put your machine to sleep and then resume it, well, it did not update its time. So it could be that actually it happened that it passed hours when your machine was resumed and you still thought that, well, it was just a second or something. So generally there are multiple issues with the time and we should be aware of them. However, but how can we use clock in computer science? Imagine that we want to use the wall clock. Well, there are multiple algorithms for synchronizing clocks between nodes. However, they are all based on the very similar idea that basically one computer goes to the other and asks, hey, what's the time? And the other replies with, the time is yada yada. And we do it repeatedly, like in a loop, and we just want to average the result to understand what the delay is, what the latency, network latency is. That's the basic idea. Obviously, we can't measure the latency like in a perfect way because we don't know where this latency is coming from, whether it's network traffic, which is, well, not stable, it can change between calls. Maybe it's because of the kernel scheduler, which decided to actually pause our application and then resume it at some, well, unknown point of time. Maybe it's because like the network card had some delay on the way. We just can't measure it precisely. So the only thing we can do is we can repeatedly ask for this time and then average the result. And this is what actually network time protocol does. NTP like divides all the computers around the planet in field called stratum, which is like layers. So stratum 0 is based on atomic clocks. So computers with atomic clock, they are in stratum 0 and they have like the time which we consider being precise. And then that broadcast this time to the computers which they are directly connected to, and this creates layer 1. This makes layer 1 of computers. So they are like one step ahead from the atomic clock. Then in turn, this stratum 1 broadcasts the signal to stratum 2, and so on and so on. This is what NTP does, and it's all based on the same principle. Even though NTP uses slightly more sophisticated formula for calculating the time and measuring the delay and all that stuff, it's generally all based on the same idea. Hey, what's the time? The time is. And we just ask this over and over again. Obviously, there are also other approaches, other algorithms which try to estimate the time a little better, or which want to cut on the broadcasting connections or whatever. But generally, they are all based on exactly the same approach. However, there is one more interesting way of handling the time, and it's devised by Google, and it's called true time. So, true time, what they do is they attach an atomic clock to every single computer in their cluster. And now, when they want to communicate or order events in the cluster, what they do is they rely on the wall clock because they can cap the maximum delay or the maximum precision of all the atomic clock readings. And it's currently capped to something like 7 milliseconds. So when you read your clock, and then you wait for 7 milliseconds and observes what happened in the cluster, then you can be sure that whether something did happen and break your transaction, or whether nothing happened, and you have a guarantee like this one. This requires unfortunately, this requires quite a significant amount of hardware, meaning that you need to have an atomic clock, you need to have a very solid and reliable network connectivity, and you also have this assumption that all your network and all your hardware things, they do work correctly, which may not always be the case, and definitely is not the case when we are talking about synchronizing cluster around the globe, meaning some machines in the US and some of them in Europe, some of them in Asia, right? We just can't do that. This can be used only in a very specific scenarios for which we can get more like better assumptions. Okay, it took a while, but I hope I convinced you a little bit that clocking computer science might not be a good idea. So the question is, how do we avoid it? And what we would like to do is we would like to build a clock which is a logical clock, not a physical clock. Okay, so we want to be able to just order events, and by ordering we mean that we want to be able to tell whether one specific event A happened before specific event B. We want to do it on multiple machines across the internet. We want it to be fast, reliable, and done by the book, obviously. However, important assumption here is we are doing that just for the events of one particular flow, meaning we are talking about events for the same transaction, logical transaction, database transaction, or the same workflow, something spanning just for one client. Imagine a situation that we run an e-commerce application and we have two clients coming to the service, both of them trying to buy something. What we want to do is we want to get a workflow for the first client and be able to order all the events for that workflow. We are not interested whether those events happened before events of the second customer or later or whatever. That we are not solving. What we are solving is just this one single workflow. And for all the events inside this workflow, we would like to be able to tell whether event A happened before event B. And the way we are going to do this is we are going to implement a thing called Lamport timestamp. So we will be saying that event A influenced event B, and we will be indicating that with this one little arrow. Okay, and we want to have this like mathematical notation, and we would like to be able to tell that A influenced event B. How do we do that? Well, instead of going through textual explanation, let's go with some slides. So imagine that we have three different nodes here, okay? So we have node first, second, and third, and all of them, they have their own logical clock. This could be wall clock, could be CPU ticks, frequency, whatever you imagine. Doesn't matter. What matters is basically is just a number, okay? Like just an integer. And we can see that first node runs with resolution of 6, okay? So it increases its values by 6, okay? So we get 0, 6, 12, 18, 24. Second node goes with resolution of 8, so we have 0, 8, 16, 24. And the third node goes with resolution of 10, okay? So imagine now that we do not use the Lamport timestamp, but we just go with the regular clock. So if we send a message from node 1 to node B, like this message A, then it's all good. It was sent at the time 6 and received at the time 16. That's okay. Same goes for message B. It was sent at 24, received at 40. So far, so good. However, problems begin when we go with replies, responses. We can see that message C was sent at time 60, but was received at time 56. So it was received before it was actually sent. This is what we can get if we rely on the ordering with using just the wall clock. What we can do instead is we can implement a Lamport timestamp. So now, this time what we'll be doing is with the message A and B and C and all the others, we'll be sending not only the message content, but also the logical time of when the message was sent. And then the receiving node will compare its local time with the one it received, and then it takes a maximum of those two values and increases it. So we can see what happens. First, with message A, it's exactly the same. It was sent at a time 6, received at time 16. It's cool. Same for B. Sent at 24, received at 40. It's all okay. But when it comes to message C, it was sent at a time 60. Normally, it would be received at a time 56, okay? So now the second node compares 56 with 60, takes the maximum of these two values and increments it and gets with 61. So from now on, it will increase its clock by 8 because that's the resolution of node number 2, but counting from the value 61. All right, so we'll have 61, 69, 77. Then the same goes for message D. It was sent at 69 and should be received at probably something like 54 at this point. We again compare 54 with 69, get the maximum of these two and increments it. So we get with 70. So this is how we implement this approach. This is how we send those timestamps between nodes, and this allows us to like get some more details of what's going on and understand how events influence each other. And now the important part of the Lamport timestamp definition was that we wanted to be able that event A happened before event B, and so event A influenced event B. Now, what does it mean to influence an event? It means that either the event happened before on the same machine. So when we have like machine A, we can say that this event at 0 happened before event at 6 because we are running on a single CPU. We are running instructions like one by one serially. So we know what the order was, and we know that this 0 happened before this 6, okay? And we also know this 6 happened before this 12. So in turn, we know that this 0 happened before this 12, okay? Same goes for the other node. We know this 0 happened before this 8, 8 happened before 16, and yada yada. Now, when it comes to events from two different nodes, we say that if one event influenced the other if it happened before the communication was received, meaning that all those events here, they happened before all those events here because there was this communication point between those two nodes, okay? Similarly, all those events here happened before all those events here because there was this communication point, okay? And now, by transition, we can deduce that all those events here happened before all those events here because there was some transmission between those two nodes, like in between, so we can tell what happened when. However, After this transmission, after this communication, we cannot tell anything whether this event 12 happened before this event 24. We have no idea because they are on different nodes and there was no communication between them, right? So there was no communication here. We cannot tell anything about those two nodes. We can only later tell that those things happened before those things here at the bottom, but we can never correlate like those two things. We won't be able to tell which happened before. So this is what Lamport timestamp gives us. And what we can deduce now is if we can say that event A happened before event B and so A influenced B, then we know that clock of event A is less than the clock of event B. This is what we can deduce from this reasoning. So when two events influence each other, then we know that clock of one event is less than clock of the other event. And this is what we can use to order the logs, to order the events in a given workflow. How do we do that? Well, coming back to the business problem we are trying to solve, there is a client customer coming to our e-commerce platform and he wants to buy something. Now, he clicks a button and the workflow starts. There is some database communication, sending an email, like charging the credit card or whatever else. And what we now need to do is we want to understand what happened before, what was the order of those events, right? Because maybe at some point something got broken and the customer tells us, hey, it broke, right? And we need to be able to tell what exactly happened. So we now want to implement this Lamport timestamping logic inside our system to understand, to order those events and figure out what was the order or how the logs, how they should be structured so we know what was going on. So there are two more important things we'll need to use in the actual implementation. First of them, well, being the logical time we just covered, and the second of them being a correlation ID. So we need to have a unique identifier for the flow, for the logical flow, for instance, like the payment flow, or maybe like, buying something in the e-commerce platform. So there must be a single identifier correlation ID, basically unique and strictly identifying what's going on. Importantly, this correlation ID cannot be modified ever. It must be always the same inside a given workflow. It must be generated at the very beginning of the workflow, and it must be sent across all the involved parties, no matter what they are. It could be database, a queuing system, notification service, text messaging service like ability or payment to charge the client, whatever. All of them need to share the same correlation ID so we can extract events for a given workflow. And the logical time, which we just covered, important part is it's local to the machine, just as we've seen in the slide, right? Each node has its own logical time, and the time is being updated in communication points. Now, how do we implement that? Let's say that we are going with some like C sharpish implementation. We just have an interface correlator which supports the get correlation ID. So basically, we have the correlation ID like a method for getting the ID, and we have two methods for like getting the logical time and updating the logical time, okay, with new value. Whether you store the correlation ID as a string, as a GUID, doesn't matter. You can use whatever you want. It just needs to be unique. That's the only thing. When it comes to the time, you can use integers, you can use longs, you can use whatever you wish. Just keep in mind it shouldn't overflow because then it will break your things probably. So generally just go with something which is safe for your situation. And the other thing which might be useful is just like the activity name, logical name of what we are doing, like charging the client or maybe adding a record to the database. Okay, so this is where we start, and we would like to have the like a basic implementation for that, which will be reused across all the systems in the cluster. No matter whether it's database, whether it's queuing system, whether it's load balancer, it needs to go with exactly the same logic. And this logic, the most important piece of it, is basically how we update the logical time. Okay, so we can just go with locking or whatever. We can use interlocked operations. What we basically do is we have a local time, local logical time, and we get a new value. We calculate the new value for the logical time, and we then try to store it like in a concurrent safe scenario. Okay, that's it. That's all we need to do. Now, Having this thingy, what we need to do next is we need to propagate those in our cluster, in our computer system, okay? So the way we do it is, let's skip the Java implementation. We would like to be able to log events using that logical timestamping, okay? So the way we need to do it is we have some iLogger interface, doesn't matter what library you use. We'll get to some practical considerations a little later, but you just need to have some logical interface for logging, which is capable of logging a message, whatever string, with some log level, etc., etc., and it has this correlator which we just implemented. Okay. Now, when it comes to what should we log to get our logs clear, the typical things I generally recommend is first log the timestamp, like the wall clock, because well, for us humans it's just readable, obviously. So it's better to have this logical timestamp probably stored as UTC, so you can convert it to your local time easily without getting all the hassle of like daylight saving times and all that stuff. Okay, then some string representing the application name. This could be, for instance, load balancer, database, web server, queue, processing messages, service, whatever. Just a name, logical, so you know what that is. Instance ID. If you do have multiple machines, then obviously some instance ID is super useful, because then you can observe actually if you had a sticky session or maybe you didn't have a sticky session, or which actually host did handle the message, so you can debug it a little later, or you know where you should go for logs to find them like on local drive. So generally instance ID is also super useful. Manage thread ID or whatever operating system level thread ID, or maybe all of them if there are multiple of those, generally log them. This is super useful, especially when we are talking about like analyzing memory dumps. Okay, when we capture a memory dump and later analyze it, it's better for us to understand which thread was processing what. Also, you may want to store a thread name. This is also again useful for analyzing memory dumps, because then you not only see what the thread is doing, because you have a memory dump, you have call stack and all the details, but also you know what it's supposed to be doing, because you know what the name is. And it's not very rare that threads actually do other things, not the things we imagine that they should be doing. Again, a couple other things for the business activity. Most important is obviously correlation ID. This needs to be stored. This is a unique identifier which we need to have in our logs. Level for like being able to tell info messages from warnings or errors. Activity like human readable name of what I'm doing, processing the payment, charging the client or whatever, and obviously the logical time, right? We do like format those things in any way you wish, whatever library you wish. They can be like bracket separated, comma separated, whatever. Just log them in a way so it's easy for you to parse them and use them later. Now, how do we use this in our system? When the customer comes to our application and clicks like a purchase button or whatever, we probably hit the load balancer, right, for the sticky session or whatever. This is the time we need to generate the correlation ID and the logical time. So it's probably some web server you are doing that. So we can go with like correlator for your web application, which creates like a correlation ID by doing GUID, MUGUID, or whatever else. And obviously the correlation time, the logical time, we already initialize in like the base class. Notice that this memory-based correlator inherits from like the correlator, the one we just implemented before, okay? Now, whenever the load balancer or any other node starts calling someone else, this could be another web server over REST API, or maybe some RPC invocation, or maybe database, or maybe this would be a message queue, or maybe service bus, or maybe not as like SNS notification, or maybe text message, or maybe some batch file stored on an FTP drive, or maybe like interactive connection or some user connection, yada yada. You get the idea? You need to pass the correlation ID and logical time. Okay, so what we can do most of the times when we are talking about HTTP is we probably are calling this over REST API or whatever, right? So we just add two headers to the request, and we add both the correlation ID and the like logical time correlation counter. Okay, we start calling, and then the receiver on the other end, what needs to do is they need to get the request, parse those headers, and update their logical time. Again, that could be an HTTP server. So what we are doing is we have some like correlator, which is getting the headers from like HTTP context and then updating those things. And the same goes for correlation ID. We get that correlation ID from HTTP headers, and we just update or we just store it locally for the given request for the given workflow. And then going back happens exactly the same. When we now send the reply back, we need to do exactly the same. We need to attach the correlation time, so the logical time, Lamport time. We can add the correlation ID again. That doesn't break a thing. It may just incur a little bigger like network usage, but generally we need to add those things back and then parse them again. Okay, so we need to parse them on the caller side, so the one originated the call, and we just parse it, and that's it. So this is how we do those things. And when it comes to important remarks, all nodes, all systems, all services, they need to use it exactly in the same way, in a uniform way. Meaning that if you are sending like a queue message, some metadata on the queue must be also tuned to support those things. Maybe you are sending it over service bus. Again, maybe some enveloping, maybe some XML tags. You need to attach those information. If you have your own proprietary RPC framework in the company, ideally it should support all of that. It's good if you hide those things in like dependency injection or other middleware, then it's basically transparent for your application code and it works for you, right? But once we wire this up across all the servers in our application, what happens next is we can just order those things and we can clean the logs. So this is a screenshot from like CloudWatch, AWS CloudWatch. Obviously, you can use whatever stack you have, like Elk Stack or whatever Microsoft Management Studio, whatever it was called. And now you can, the only thing you need to do is you filter your events based on the correlation ID, and then you order them based on the logical time. So you can see that even though some events like are out of order when it comes to the wall clock, they are still in order when it comes to the logical time. So based on that, we can not only see what was happening, like we have a message, we have the activity, we have all the informations, we know who created this event, but we also can order them based on the actual events, how they happened. So this is what we can do, and this is how we get to the spot when we have all the events like ordered and readable. And important remark is, for many years, this was something you had to implement on your own. However, quite recently, W3C introduced a thing called trace ID, which is basically some sort of correlation ID, which we can use to order the events in a similar way. The approach they took is they are storing the trace ID like a stack, so you can have multiple those correlation IDs. So it's like basically a call stack of execution. This gives you some understanding of what was happening, but it doesn't tell you exactly which things were happening, like in terms of multi-threading scenario or in terms whether those some things are shared by like multiple nodes. Generally, that's a good step forward, and we all should be using this trace ID where it's possible to propagate the correlation ID, but still we don't have the full logical counter yet to do the Lamport timestamp. But still, multiple frameworks started supporting that, so you may be even using that without noticing it. And now we solve this one problem for one workflow. Now, question is, can we solve exactly the same for multiple workflows? Can we tell that when two customers came to the system, and can we tell whether events of customer number one happened before events of customer number B? And this is going beyond time. I won't be covering that extensively. I will just give you a brief idea how we can solve this and what we can solve on the way as we are doing with that. The thing we can implement apart from Lamport timestamp is a vector clock. So a vector clock is similar idea to Lamport timestamps, only this time we have clocks for all the nodes, meaning that node A stores not only its own clock, but also clocks of other nodes like nodes B and C. And when communication happens, nodes exchange all of their clocks. So node A sends all 3 clocks to the node B when it communicates with it. Okay, this is what we can do. And now this gives us a super important property, something we didn't have with Lamport timestamp. What we did have with Lamport timestamp is when event A influenced event B, then we knew the clock of A was less than clock of B. However, with vector clocks, what we can tell is the opposite. If vector clock of A is less than vector clock of B, then A happened before B. And this is something we don't have with Lamport timestamp, but we do have it with vector clocks. The problem is creates tons of communication. Even though there are multiple algorithms for multiple various clocks, we just can't use it super easily because it's slow and it takes a lot of network. But it allows us to solve a yet another super important problem, which is Byzantine generals problem. So there is a story that when multiple nodes want to agree on something and there is a malicious node, so basically a malicious in terms of not working correctly, then they can't agree on that easily because they get different results. And in distributed systems, components do fail. They may stop responding, the network may go down, they may repeat messages, they may violate the protocol. Multiple things can happen. So we need to understand that the failure is basically inherent to all the distributed systems. And that's why we introduce a notion of k-fold tolerance system, which means that if at most k nodes, k components fail, then the system still works. And to basically solve the Byzantine generals problem when any node can go down anytime with no any predictable reason, we need to understand that we need to solve basically a consensus problem. And consensus problem is a decision in distributed system which has some fancy properties, like we would like it to be terminated in some finite time, so it finishes in a finite time, and also all the nodes agree on the same value, and the value is proposed by some nodes, so generally some mathematical properties. And now to understand that is when we guarantee that at most k nodes get down or go down at any point of time, then we need 3k plus 1 components, 3k plus 1 nodes to guarantee that the system just works. However, but if we cannot guarantee bounded message delivery, so it may be that we send a message and it gets to the destination a month from now, then technically we may not be able to solve the consensus problem at all. And this is computer science, this is maths, this is something which has been proven that you won't be able to solve the problem. Meaning that if you have those two customers buying the same item and you want to understand who was the first one to do that, it may not be possible to be solved at all, depending on what your environment is. There is an algorithm for tackling that. It's called draft, but generally implementing those things is hard. But once we implement that, we solve a couple other problems. So this is more reading for you. However, if you ever try to tackle this, important thing to understand is it's super hard. And this is even a project called Jepsen, which tries to guarantee or verify specifications of distributed databases, MongoDB, and others to confirm or deny whether they hold up to their agreements, to their guarantees that they do not lose data, and all that stuff. And summary, while clock is hard, synchronizing clocks is even harder. Time zones are tricky. We need to use logical clocks because, well, the world won't be easier. And especially when we start traveling the space, going to Mars or other planets, it won't get easier. The world will be distributed even more. So generally, use those logical times and be aware of how we can use them. That's it when it comes to this talk. If there are some questions, I'm happy to take them now, and we can also then move on to the discussion. At the end of this talk, there are a couple of references for you, books you can read, and that would be it. Do we happen to have any questions?
Thank you for your talk, Adam. This topic is very close to me. My current project is not very big, and it is hosted in 2 data centers and a couple of dozen servers. But even in this simple configuration, we run into such problems when trying to investigate some incidents in a production environment. And of course, we use correlation IDs, and I must say, often it's very tricky to order log entries. And mostly it happens in high performance services with low latencies, so where differences between operations is very small, and I always see these effects all you mentioned before. And as you said, NTP is not ideal. So
Yep.
now we have only one solution. It's just knowledge about business domain and our infrastructure, but it's not scalable. It's very tricky and it's very difficult. Thank you again for your ideas. Now I know what kind of stuff I can deploy to my servers.
Cool. Glad I could help.
Thank you. Dear attendees, now we are going to discussion in Zoom. Please join us and see you there. Bye.